all Indian scientists working in this field under one umbrella and work as a team coherently and make some contribution. So that's how it was formed, and since then the group has started several activities, regular activities, and one of them is we conduct bi-weekly discussion and it has been going on since 2015, and last a couple of months back we completed 100th discussion. So it has been quite regular, and that is very helpful in a sense that in that discussion it is not so formal. We discuss our own work mostly, and then also discuss various plans and progresses, many things. Currently it is conducted by Rajesh Mondal, who is a postdoc at Stockholm University now. And then we also started observational program with UGMRT mainly, and this is led by Arnav Chakraborty, Ohirup from IIT Indore, and Nirupam. They are the main people who are leading this, but there are other people also helping in this program. And we have observed with GMRT and also published some very interesting results. And we used to continue our observational program. We used to observe more with GMRT. And so there is a discussion session at the last day of this conference, and we would like to discuss this observational program more. So I would request you to be there and participate actively in the discussion. So apart from that, we also organize such kind of workshops and schools, as you heard from Akanksha. So this is, I think, fourth or fifth workshop that we organize regularly, and we also discuss mostly our own work. And that help us to know each other, the work from other group members. And sometimes it helps to trigger collaborations. So we have now been collaborating with other members extensively. So we are working as a team, really. We are not competitors, but we are now collaborators. So that's I think that's one of the achievements of this group. So regarding this group, so you know this such kind of workshop is essentially provides you a platform that where you can discuss your ongoing work and also explore possibilities of further collaboration. So I request all of you, particularly the young members of the group, to engage in discussion actively. Don't hesitate to ask questions, even if you feel those are very basics. Because by that way we can make it more engaging and successful event. And at the end of this workshop, at the last day, last session, we have a dedicated discussion session, and for soon, and I am supposed to conduct that session, but it's just other people can also participate in that. To discuss our future plans, future projects. So I remember last time we had such kind of future planning back in 2015 or 16, maybe 16. And we listed the projects, number of projects that we can pursue. And I'm happy to see that list that 80% of them actually we have completed. So now it's time to make another list and work towards this for the next 2-3 years. So with this, I end here, and I hope this workshop will be enjoyable to all of you over the next 4 or 5 days. Thank you, Akanksha.
Thanks, Kanan. So one thing I forgot to mention, so every invited talk is for 30 minutes followed by a 10 minutes question and answer session. And every contributory talk is for 20 minutes, followed by a 5-minute question and answer session. So let's start with the first session, and I request the Thankar Roy Chaudhary from NCRA to please chair the session.
Just to correct, the talk is the invited talk is for 30 minutes, including the question and answer session.
Yes. Sorry, I think there is a confusion. So I see the invited talk to be of 40 minutes in total. So shouldn't it be 30 plus 10?
Sorry, 30 plus 10. Sorry.
Yeah, and I see the contributor talks to be of 20 minutes in total. So should it be 15 plus 5?
Yes, sorry.
Yeah, okay, fine. So that helps me at least. So Suman, Suman Chatterjee, can you stop sharing the screen? And I request Suman Majumdar to share his screen. So welcome everyone. So we will start the first academic session of the workshop now. And we will be having 3 talks. The first one is an invited talk, followed by 2 contributed talks. And basically the theme would be 21 centimeter signal with simulations and various statistics which can be done with it. So the first talk will be the invited one by Suman Majumdar of IIT Indore. And he will be summarizing discussions on cosmic dawn and reionization, theory, simulations, and astrophysics.
Suman, I did not have the permission to share my screen.
Okay.
Now I got it. Just a second.
Yeah. That's okay. So Suman, I will. Your talk is of 30 minutes. So I will give you a warning at 25 minutes.
Okay. Thank you very much.
Yeah.
So
you can start.
Okay. Just let me start.
Yeah, perfect. Please go ahead.
Okay. I hope everyone can see the slides. Okay. So I would like to first thank the organizers for allowing me to give a talk here, for particularly inviting me to give a talk here. And I would just like to mention that the last workshop of this series was in IIT Indore, and many of you actually had attended that one. It was just before the pandemic. Probably it was the last workshop before the pandemic, at least in US, maybe in India at least. Okay, so I was given the task to essentially summarize about the motivation or summarize about what are the progresses in simulation, modeling, and how you can infer astrophysical, let's say, information out of this simulation, modeling, and observation of cosmic dawn and epoch of reionization. So what I decided, because it's such a vast topic, it is difficult to cover everything within 30 minutes. So what I took the liberty to essentially touch upon different approach. First of all, to give a brief overview or motivation, why do we need any kind of analytical or numerical modeling for the signals from the cosmic dawn and epoch of reionization. And the next thing is how we can use those models to infer about the parameters of cosmic dawn and epoch of reionization. When I say parameter, it can be parameters of the intergalactic medium or the sources of the reionization or cosmic dawn. How one can use these models to infer about the properties of these sources as well as the intergalactic medium. So I will touch upon a different kind of modeling techniques very briefly. Then I will essentially discuss a few example cases where these techniques are used with some statistics to constrain the model parameters or distinguish between different kind of models. So that is more or less the plan of my talk. So as this is the first talk of this conference, so I took the liberty to give a broad overview of why we are all gathering here. So as we all know that the earliest image or the detailed image of the universe that we can have at the present day is the image of the cosmic background, micro background radiation, where we can measure the temperature fluctuation of the order of 1 parts per million. And this was the stage when universe was 10 to the power 6 years, of the order of 10 to the power 6 years old. That is approximately redshift 1100. So this particular image or the map essentially tells us what was the level of fluctuation present in the matter and radiation when matter and radiation just got decoupled. So essentially, this is an imprint of those fluctuation on the radiation itself, that primordial radiation, that is cosmic microwave background radiation. The other detailed picture of our present-day universe that we have is the distribution of galaxies around us. So that tells us how galaxies are distributed around us. Let's say this is our present-day location, this redshift 0, and each dot here represents one galaxy. So essentially, it tells us that galaxies are distributed. If I consider most of the mass is within the galaxies, most of the visible mass is within the galaxies, then they are distributed in a complex wave-like fashion that is popularly known as cosmic wave. So the question or the puzzle that remains there is that how we manage to come from these tiny bits of fluctuations in matter to this complex distribution of matter that we see around us today. So to answer that question, you need to know what might have happened in between these two phases. So what might have happened in between, that can be described using this artist's impression, where on the left-hand side, we have our cosmic microwave background radiation, and on the right-hand side, we have the distribution of galaxies at present day. So what might have happened in between these two phases is the following, that the tiny bits of fluctuation that was there in the matter, they gradually grew with time under gravity, and they formed the very first collapsed objects. And these are bound objects. Most of the matter was dark matter, so these bound objects were so-called dark matter halos. Now, inside these, because the baryon will follow the dark matter in large length scale, so baryon essentially followed these dark matter halos and formed the very first stars or luminous objects inside, which are hosted in these dark matter halos. So these very first stars emitted huge amount of radiation in ultraviolet and X-ray wavelengths, and these radiations heated as well as ionized their surrounding intergalactic medium. So once this first generation of stars, so-called population 3 stars, died, the next generation of stars and galaxies were formed, and they keep on producing this ionizing and heating radiation to heat up the cold intergalactic medium, which was cold simply because of the fact that radiation was decoupled from it significantly. It is not any longer coupled with it. And gradually, the ionized regions and the heated regions around these very first sources or the next generation of sources grew in size, and finally they overlap with each other, and most of the intergalactic medium turned ionized. And when I am talking about matter getting ionized from its neutral stage, I am talking about the baryons, and among the baryons, the most of the baryons are as hydrogen. 3/4 of the baryons are hydrogen. So this is essentially hydrogen getting ionized. Now, why do you call it reionization? Because most of the baryons were ionized before the last scattering surface. So this is the second time they are getting ionized. That's why they are called, this particular process is called reionization. So the very first, when we get our very first stars, that is the time which is popularly known as the first dawn or the cosmic dawn. And when these first stars, which were initially mostly active in heating up the intergalactic medium, later on they became they started ionizing the intergalactic medium. This particular period from when they are formed and till they start ionizing the intergalactic medium significantly is popularly known as cosmic dawn. And the next phase, when they are mostly working as the ionizing sources, is popularly known as the epoch of reionization. So CD and EOR. So now the next question is, as it is a puzzle, so for any kind of this sort of puzzle, you need to answer 3 basic questions: who, when, and how. So who was getting ionized here? Let's say hydrogen and also helium, though I will not speak about helium reionization in this talk, but that is also important. Next is when this process started and when it ended. So that particular time period, and whether it was happening at a constant rate or at a variable rate. All those things are also important to understand the whole process. And third is, what are the physical processes that are influencing this reionization? So all these three questions we need to understand. And that essentially builds our motivation for modeling, or let's say simulating, the epoch of reionization. But before we go into simulation, because simulations are only useful if you have some sort of observation to essentially use your simulation to constrain those observations or extract information from those observations. So there can be two kinds of observations of epoch of reionization, let's say broadly speaking. One is in which you are targeting to observe the intergalactic medium, and the second one is where you are targeting to observe the sources of ionization or heating. So, or the first luminous sources, let us say. So if I think about how we can see the intergalactic medium, there are various ways. Many of them are, let's say, so-called indirect way, but many people can argue that they are also direct way. And I'm not going into that particular argument right now. So one is this, if you look at the spectra of very high redshift quasars, so what you will see is that the more the local intergalactic medium around that quasar is ionized, the more emission you will see on the left-hand side of the Lyman alpha peak. Otherwise, if there are neutral regions on the path of the ray of the quasar that is coming to you, that in those locations you will see absorption troughs. And these absorption troughs will become completely dark. Basically, it will give you a zero emissivity or zero flux only when the corresponding neutral fraction of that particular hydrogen cloud or whatever obstructing your view of the quasar is above 10 to the power minus 4. The neutral fraction is roughly about 10 to the power minus 4. So it can tell you to some extent, and also from the shape of this absorption trough near the Lyman alpha peak, you can essentially tell what is the limiting value of neutral fraction. You can put some sort of limit on the neutral fraction value around the local IGM of the high redshift quasar. Now, there are certain drawbacks in this kind of observation. First of all, these are pencil beam observation, because this is a single line of sight observation that you are getting for one quasar. Unless you have within the same redshift range a significant amount of quasar, it is very difficult to say what is the global neutral fraction or global state of ionization of that particular within that redshift range. The second problem is this saturation of this Gunn-Peterson trough. So, as I said, that if the neutral fraction of the local IGM is just above 10 to the power minus 4, the entire flux can get absorbed. So it is difficult to say just from the absorption trough itself whether the neutral fraction is 10 to the power minus 4 or 0.1 or let's say 1. So you can put some sort of limit on the neutral fraction, but you cannot do anything probably beyond that. But there will be discussion on this particular observable, and you should check out the talks by Girish Kulkarni and Janki Raste on that. So the next one, which has been used for almost a decade, is using the Thomson scattering optical depth of CMBR photon. It gives you an integrated number along the line of sight. So it tells you essentially, given that reionization was sort of a step function, reionization history is some sort of a step function, it tells you within what redshift range reionization might have happened, or instantaneously at what redshift reionization might have happened. So it also puts some sort of a weaker constraint on reionization. However, if you combine all of these and many other observations together, you may be able to put a bit more tighter constraint on reionization history. And Otridev Chatterjee is going to discuss that in his talk. Next, most of the talks in this particular workshop will be dedicated on, particularly at this approach, is try to look at the baryons, the most prominent baryons, that is hydrogen, in the intergalactic medium. So if you can see the hydrogen through its hyperfine transition line, which has a wavelength 21 centimeter, you will be able to, in principle, map the hydrogen distribution or its density distribution over a large redshift range using, let's say, future observations of this particular era, if you have sensitive enough and precise enough measurement of this particular signal. And as I said, most of the talks are dedicated or focused at particularly this approach of observing the cosmic dawn and epoch of reionization. Then, if you think about observing the luminous sources, then you can try to think of very high redshift Lyman alpha emitters. So these are high redshift, extremely bright galaxies that you are looking at. You can use Hubble Ultraviolet Field or even Subaru Hyper Supreme Camp to look at these galaxies, and you can try to figure out what is their luminosity function and how their luminosity function evolves with evolving redshift. If you can get a hold of that, and if you try to model their luminosity function using your analytical model or your simulations, etc., you can get a hold on some sort of star formation rate that they have at those redshift, and how the star formation rate is evolving with redshift. So that actually tells you about whether these high redshift, bright, extremely bright Lyman alpha emitters are the major sources of reionization, or they are very insignificant in terms of the ionizing photon budget for reionization. Or in the other hand, whether most of the galaxies that are responsible for reionization are presently invisible. They are so faint that we can't see them in this method. So that is one way of looking at the sources of reionization. The other way is you do not target to resolve individual galaxies, whether spectroscopically or photometrically. What you try to do is try to see the emission from a collection of galaxies. So it is some sort of coarse gridded imaging technique where you target a particular spectral line. In this case, you target, let's say, the singly ionized carbon or carbon monoxide line coming from these early galaxies. And your aim here is not to resolve individual galaxies, but to get an average emission from a bunch of galaxies within a coarse gridded pixel within your observation. And this approach has been discussed by Silva et al. And Bong et al., etc. And you should check also the talk by Chandrasekhar Murmu, who is going to speak about this in this particular workshop. And this actually gives you an alternative way to look at the sources of reionization. And there are several upcoming instruments, for example, Concerto, I think, then Time Pilot, etc., which are CC80 prime in Atacama Large Millimeter Array. So these instruments are planning to map the C2 emission from early galaxies using this intensity mapping technique. And one can combine the intensity mapping of C2 as well as the 21 centimeter emission from IGM and cross-correlate them and get a better constraint on various kinds of parameters of reionization as well as cosmic dawn. That could be a future goal. So, where do our modeling comes into the picture? So, the major motivation in modeling the epoch of reionization or the signals from epoch of reionization is the following. You have your observables. Now, these observables I just kind of listed out. There can be various kinds of observables, whether you are targeting the IGM or you are targeting the sources of reionization. Based on that, the observable can vary. You define a statistic out of the observable that you have targeted in your observation, and then you also define a model which gives you a simulated or analytical form of that particular observable or that particular statistics derived from that observable. And then you compare the observed statistics with your model statistics under a Bayesian or any kind of statistical framework to constrain. If you are assuming that there is only one model for reionization, then in constraining the parameters of that model, Or if you assume that there are several models of reionization and you want to find out which one is the most favored model, you can do a model selection as well. So you should check out the talks by Utridev Chatterjee, as well as I think Girish will also speak about this, about combining different kind of observations and constraining the parameters of reionization under various kind of statistical framework. So there, the most important part, that is the focus of this particular talk, is that you need to have some sort of physically motivated analytical or numerical model for the signal that is coming from your cosmic dawn or the epoch of reionization. So now, when it comes to modeling the signal, ideally one would like to model the source properties as well as the physical processes that are going on in the intergalactic medium from the very first principles. But there is a problem of scale. So in principle, to do this, one would need to simulate the physics from the scale of galaxies, that is few kiloparsec or smaller, to the cosmological scale, that is hundreds of megaparsec to 1 gigaparsec or more. And this has been the most challenging, let's say, obstacle that people are facing so far. The other problem that generally gets ignored is that just simulating one model is not enough. As we were talking about this constraining models under a statistical framework, that requires you need to simulate this model again and again, probably millions of times or even more, for putting some sort of constraint on your signal or CDO or model parameter. So the optimal modeling of the signal from this particular age or era depends on what exactly you would like to do with the signal. And depending on your motivation, the approach in modeling the signal will change. Where you can basically give up some accuracy or small scale physics, and where you cannot, that actually is dictated by what you would like to do with the signal in the end. And that is the basic motivation, and I would like to stress on that particular point specifically, because we forget about that quite often. So, for example, analytical models of reionization. This essentially is very simple, where you define all your physical processes in terms of different terms. You have your ionization, your recombination terms, your heating terms, as well as there is spin temperature fluctuation, which we will come later, and probably other speakers in this session will speak about them, so I will not go into the details. So all of those terms can be modeled analytically, and you can have a coherent equation which represent the signal from a particular redshift. Now, this kind of analytical model can be completely fine if you are, let's say, dealing with the global signal. For example, you are looking at the sky average signal, that sky average 21 centimeter signal that is coming from CDOR, then probably this kind of analytical model is good enough. And or let's say you are trying to put constraint using several observables, and for example, the CMBR, as well as the Lyman alpha Lyman alpha emitters, as well as your quasar absorption spectra, or all these things, along with, let's say, 21 centimeter global signal. So then simulating each of these signals and corresponding statistics individually, and that too for a large number of points in your parameter space. And when I say large number of points, that could be millions and millions of points, because if you are doing an MCMC analysis, you are taking millions of random steps. So at every step, you need to simulate the signal, all the signals that you are involving in your parameter estimation framework. It will take a huge amount of computing time. Instead of doing that, you can actually use safely a analytical model and probably still get a reasonably good constraint on your UR parameters, both source as well as IGM parameters. And one should check Utridev Chatterjee, Shikhar Mittal, as well as Ankita Bera's talk on this particular regard. They will speak about the analytical models of cosmic dawn, as well as in the context of global signal, and when there are interesting IGM physics going on. Next, if you are interested in the spatial fluctuations of a particular signal, for example, the 21 centimeter signal coming from the CDOR, then as a function of cosmic time or redshift, then you would like to have a good hold on the IGM physics. So then the radiative transfer models or simulations become very useful. In this particular simulation, you follow the path of each individual ultraviolet or X-ray photon and solve the radiative transfer equation on its way. In this case, the modeling of the IGM physics, as I said, will be very accurate, but sometimes the modeling of the source properties may have some sort of limitation. You may assume some sort of a uniform spectra or some sort of mass-dependent spectra of your sources, or you just generate a lookup table from where you just pick up the spectra, or you average out the spectra. You do not even separate different frequencies of photons separately. You do not treat different frequencies of photons separately. Instead, you say that, okay, if photons are within this energy range, I will treat them in this way. If the photons are within this energy range, I will treat them in this way. So the source modeling is somewhat, let's say, approximate. Still, it is quite good, but the IGM physics here is implemented quite well. So this is important when you are looking at simulating the signal from that is coming from the intergalactic media. Also, there is semi-numerical simulations where both the IGM physics as well as the source properties are approximated to gain in terms of computing time. Because in case of radiative transfer models as well, if you want to simulate, let's say, millions of steps in your parameter space, that will take a significant amount of time. Otherwise, what you can do, you can essentially calculate some sort of average number of photons that are contributing towards heating as well as ionization, and define the temperature as well as the ionization state of each individual pixel in your simulation box. And this method has been used quite in most of the time in most of the statistical analysis people do nowadays. And it allows us simply because it is faster to simulate the signal in this way. That's why it allows us to generate several statistically independent realization. It is not only about simulating, let's say, millions of points in your parameter space. You can even calculate the cosmic variance, because you can generate at the same parameter point, same point in the parameter space, you can generate, let's say, thousands of simulations and then take the average and the variance as the mean cosmic signal on top of the cosmic variance. So Borun Maiti is going to speak about this type of simulation later in this conference. So this is semi-numerical simulation, but what is happening recently in this field is essentially there is a burst of activity where people are using artificial neural network to emulate the signal that is coming from the early universe. Now, this emulation of the signal or the
sorry, you have 5 minutes.
I have 5 minutes. Okay, fine. I will finish very quickly. So this emulation of the signal also requires your basic matter density field, where you need to simulate the matter density using a n-body simulation, as well as you need to identify your sources of reionization and heating. And you can train your artificial neural network using a simulated, let's say, a radiative transfer simulation of the CDOR. You can train your artificial neural network in how this density and source field translate into a reionization map or a signal map. And in turn, if you provide any random density and source field later to the trained neural network, it will provide an output in terms of your expected signal map. And this is being done by Sharding et al. In 2009. Also, there is a slightly different and easier approach for emulating the signal, where you do not care about emulating the entire signal map, rather than you focus on emulating the specific signal statistics. And in this case, for example, Smith and Pritchard has done that. using same an artificial neural network structure where you train your neural network for a given set of parameters how the specific statistics looks like. You basically provide these two information as input, and once the neural network is trained, it produces output for any given parameter sets within the range of parameters where you have trained your neural network. You should check Madhurima Choudhury's talk on this particular regard. So as time is short, I will just do a bit of self-promotion, which is essentially the application of these simulation techniques in various aspects of observing the CDOR. So the first point that I wanted to make is that the 21 centimeter signal that we are observing is non-Gaussian in nature. That's why so far most of the parameter estimation is done using the power spectrum of the 21 centimeter signal. But power spectrum will not be able to constrain the parameters well, simply because of the fact that power spectrum do not encapsulate the non-Gaussianity in the present in the signal, and this non-Gaussianity is arising due to the fluctuating due to the growing ionized and neutral regions, basically growing ionized regions in the IGM with time. So the non-Gaussianity is also evolving with time, and that one can estimate using various statistics. Some of them are listed here, but I would like to focus on a statistic called bispectrum, which one can use essentially by combining the signal in 3 different K modes in Fourier space, taking product of the Fourier transform of the signal in 3 different K modes, which form a closed triangle. And as you can imagine, there can be various kinds of triangles. So one need to figure out which are the unique triangles in the Fourier space. So Abinash Kumar Shaw and Mohd Kamran will speak about it. I will just quickly like to tell you that if you use this particular statistics, what I was trying to stress upon, that you will be able to constrain the CDUR parameter better compared to the power spectrum. And this was shown by a master student at IIT Indore, Himanshu Tiwari, where he developed a emulator for 21 centimeter bispectrum for the EOR 21 centimeter bispectrum using a semi-numerical simulation of the signal, and he showed that the power spectrum can be emulated quite well as this bispectrum also can be emulated quite well. Then using this emulated bispectrum as the model, he tried to constrain some observed, tried to constrain the UR parameter from some observed bispectrum. And as it turned out that these blue contours essentially show the 1 sigma error limit error contour for bispectrum, and the yellow ones are essentially same obtained from the power spectrum. As you can see, the bispectrum can provide a much tighter constraint, given that you consider all unique K triangles in your analysis. The same can be shown here as well. And another master student, Anchal Saxena from IIT Indore, have also shown that one can actually distinguish between different dark matter models for structure formation using the UR21 centimeter bispectrum, much better than the power spectrum, which was mostly used earlier. So the difference in the bispectrum can be from 10 to 100% or 30 to 300%, depending on what kind of warm dark matter model you are using. So I will just stop here with the note that with the advent of SK, we will have a huge amount of data coming at our. So we would need, for this new era of data analysis, we need new tools to handle and interpret this huge wave of data. Thanks. Sorry for going over time.
Thank you, Suman. I think this was a very nice overview talk, and it helped set the context for the full workshop. So many thanks. So we have time for some questions and comments. So I can probably take. So yeah, Shantanu, please unmute yourself and go ahead. If you are Yeah, Shantanu, are you?
Yeah. So sorry, I was not able to unmute. Now I can. Yeah. So just a quick, since I
Yes.
don't work in the field, right? So one thing I didn't see anything mentioned is dark matter. So how does all this depend on, I guess, the nature of dark matter as well as non-dark matter based alternatives?
Acha,
Just a
so
high level question. So
yeah. So what we have done here, we have just considered two different kinds of warm dark matter model. And if you consider warm dark matter model, what happens that affect your structure formation. So essentially the halos, as I mentioned, the dark matter halos are the host of your luminous sources. So the formation of halos get delayed, as well as the halo mass function overall changes slightly its shape. So the evolution of the halo mass function also changes. Therefore, the UR history. So when I'm talking about UR history, it is basically average neutral fraction versus redshift. That particular quantity changes depending on what kind of dark matter model you are using. But even if you look at the same neutral fraction, what we found out that even then there is a significant amount of difference in the topology of the 21 centimeter signal. And that is coming due to the fact that even if two 21 centimeter maps have same neutral fraction, as they are at two different redshifts, the underlying halo distribution halo properties are slightly different, and that's why the topology of the 21 centimeter signal is also slightly different, and that affects its non-Gaussianity, and in turn it affects the bispectrum more compared to the power spectrum. So we see a larger deviation from the typical cold dark matter model in those cases. In brief, that is it. And if you want, we can discuss it offline or on Slack. I can point you towards the paper as
well. Any other questions? We still have some more time. Proshun, yeah, Proshun, you can go ahead.
Hi, Suman.
Yes.
So when you said that your statistics for the bispectrum is better than for the power spectrum, that is the underlying distribution is of the distribution of the parameters. It's not doesn't include the noise, measurement noise, etc. Right?
Oh yes, we have considered basically some analytical. Okay, maybe my window is not. Yeah, we have considered some analytical estimates of noise. So when this is a Bayesian inference, so in the Bayesian inference, when you are writing down the likelihood, you have a sigma, right? Observation minus model divided by the sigma. So there, the sigma, we have considered both sample variance. It is not cosmic variance. So probably Rajesh can elaborate on that better. And we have also considered an analytical tree level estimate of SK1 low noise at redshift 9 for 1000 hours of observation for both power spectrum as well as for the bispectrum. So in case of, if you want to calculate the noise in a very simplistic fashion, you can write down the sigma of bispectrum due to noise in terms of the three noise power spectrum at K1, K2, and K3, the three K modes for which you are calculating the bispectrum actually. And we have considered K modes from 0.2 MPC inverse to roughly 0.6 MPC inverse, all of which might not be observable within 1000, means if you calculate the noise correctly and very accurately, which probably Rajesh is doing, you may not observe all shapes of triangle for 0.6 MPC inverse for 1000 hours. Maybe you have to increase the observation time for that. So this analysis is for that noise consideration. From that particular.
Okay. So it includes the measurement noise also. Yeah. Thank you.
Yes.
Yeah. Our next question is from Indulekha. Yes. Indulekha, please go on. Okay, I don't see. Yeah, Indulekha, please go ahead.
Yeah, I was just wondering whether these observations and simulations going from integrated along the line of sight observations to the statistics of whatever perturbations are present. Do we gain any insight from looking at what is done in remote sensing, like imaging through turbulence? There you know the source and the results which come out of it.
Okay, so I think they are, so, okay, I should correct myself. So when I am talking about simulations, I am not talking about simulating the, let's say, response of the telescope or the response of the ionosphere, etc. So that is something
No.
different kind of simulation.
No, that is not my question.
Okay.
In going from analyzing the integrated result to the three-dimensional result, I'm assuming to some extent that might be happening.
Okay, what kind of observation you are referring to when you are talking about integrated result? Is it just the CMDR tau or
No, maybe it can be discussed later, like coming to conclusions regarding the three-dimensional characteristics of turbulence through information from a line of
okay. Again, I would suggest that you take up offline, because in this case we really do have 3D information in the data.
I understand what.
Okay.
Yeah. So, Suman, there is one question on the chat box from Sauraj Bharati. Is asking, what are the difficulties in doing small scale simulations?
So I think there are many uncertainties in the small scale simulation, and probably Tirthuda can explain it better than me. First of all, when you are doing small scale simulations, you cannot, because you want to resolve even, let's say, inside of a galaxy, you will not be able to go beyond, let's say, few megaparsec scale or more than that. And then you have to simulate the galactic dynamics as well as, let's say, star formation, etc., and various other kinds of complexities come into play. So there are people doing that. I think one could look at, for example, the papers by Jean-Peter Padre Cooper, as well as Christian Finlater, as well as these Crocs simulation by but are they doing individual galaxies? I don't know. By Nadine. But I'm not an expert on that. Probably Tirthuda can elaborate or Girish can elaborate on that.
Yeah, no, I think what you said was fine. I think, yeah, of course, in any case, the main problem would be that if you are stuck with small scale simulations, you can't study the large scales, which you already mentioned in the talk. So we need both. And then, as we all know, the small scale simulations come with their own non-linearities and other complex physics, which make it really difficult. So yes, I mean, if you are happy with only small scale studies, you can do small scale simulations, but that's not enough for cosmological studies. I think, again, Suman, this is something you mentioned nicely in the talk, so I don't have to add anything. But this is a good point to move on. Again thank Suman on everybody's behalf. And our next talk is by Abinash Shaw.
One thing I want to say. So if there are any further discussions, just go to the discussion channel, add channel in the left, and then browse all channel. You will get the discussion channel, and you can continue the discussion. Yeah.
Thanks, Shamil. So our next talk is by Abinash Shaw from IIT Kharagpur, and he will be telling us about a fast method to estimate the bin bispectrum for unique triangle configurations. Abinash, your talk is of 15 minutes. I will give you a warning at 10 minutes.
Okay, thank you, Tirthuda, and hello everyone. I'd like to thank the organizer for giving me this opportunity. So today I'll be talking about a faster method to estimate the bin bispectrum, and obviously for the unique triangle configurations. And this is an ongoing work. However, the main motivation for this work is not related to EOR, but it can be easily extended to EOR later on. So yeah, let us begin. So as we all know that the large scale data which we obtain is in form of some sort of fluctuating map, which is more or less non-Gaussian in nature. And as the previous speaker has already mentioned, that EOR signal is a highly non-Gaussian field. And people basically quantify these fluctuations using statistical tools, mostly the power spectrum. However, we have seen that the power spectrum is unable to quantify the non-Gaussianity present in the field, which can be important in case of which is important in case of EOR to model this non-Gaussianity, because it contains another extra information about the sources and the processes. So in order to capture the non-Gaussianity present in the EOR field or any other nonlinear field, one need to move to some higher order statistics like bispectrum or trispectrum. And the bispectrum is basically the 3-point statistic, which is the lowest order statistic sensitive to the non-Gaussianity in the signal, and it is defined by the product of 3 delta k's, such that their wave vectors form a closed triangle. And the delta k's are basically the Fourier transform of the fluctuating random field. Okay, so here in this analysis, we are not considering the bispectrum for each and every individual triangle. Rather, we are considering binned bispectrum estimator, where we average over the bispectrum estimate of the triangles of nearby shape and sizes. So here the summations are over all the grid points corresponding to three K bins, K1, K2, and K3. And this Kronecker delta over here takes care of the closure of the triangle. In tri, here is the total number of triangle corresponding to these 3 bins. So as we have already seen that in order to compute the bin bispectrum, we need to search for this closed triangle over gridded data or any observed data also. And let us say that we have cubical data, which there are n to the power 3 grid points. And if we search for this closed triangle within that data cube for in a direct approach method, it will take a time which scales as n to the power 6. So as mentioned by the previous speaker, that in future we are going to have a very large amount of data from the observations, SK observations or any other observations, as well as from the simulations. So there will be this number will be of the order of billions. So then you can imagine that how it will, if we go on searching for the triangle in a direct approach method, there will be a huge amount of time and it is computationally intractable. So that's why we need an efficiently fast technique to estimate the bispectrum from these data accurately. For this, we use a Fourier transform based technique, which by using which we estimate this summation in the numerator and as well as this number of triangle, which can also be recasted in a similar form as the numerator. And here we use the Fourier representation of this Kronecker delta function. And by putting this into the estimator and doing a bit of mathematical rearrangement, we finally obtain the bin bispectrum to be of this form, where there is a summation over all the real space grid, and there is a product of 3 delta kix and then I kix, where the delta kix is nothing but the inverse Fourier transform of this quantity, this product, where this delta k is the signal and this mki is the filter function corresponding to each bin. So this is defined as to be 1 within the bin and it is 0 otherwise. And these i's are nothing but the inverse Fourier transform of the this filter function itself. So here we can see that in order to compute the bispectrum, we need to have an estimate of six of these terms, which need 6 Fourier transform, which we do using the fast Fourier transform module. And the time complexity in this case is of the order of n to the power q. It scales as n to the power q, whereas this summations also scales as n to the power q. So the overall process here has now scaled down from n to the power 6 to n to the power q problem. So you can see that there is a clear advantage. This kind of estimator has been used in previous observational papers, where these guys have used the properties of the Fourier transform to estimate the Fourier statistic from the galaxy redshift survey, as well as in order to constrain the primordial non-Gaussianity, it has been applied to the CMB maps also. However, they have not clearly discussed about this the use of these methods. There have been a recent works on the theoretical side where these authors have extensively discussed this methodology in context of the 21 centimeter cosmology. However, their studies are limited to only a few types of triangle. They have not considered all types of triangle, as well as the triangles are not unique also. So in this work, we designed the estimator which can compute the bispectrum for the triangles of all possible shapes and size. By shapes and size, we mean so we basically parameterize the triangle by its size, which is given by the length of the largest side of the triangle, and the shape, which is given by the t. Shape parameters are t and mu, which is nothing but the ratio of the two largest sides and the cosine of angle between these two sides. And we also represent our bispectrum as a function of these size and shape parameters. Here we consider the triangles available in the box simulation or the observation box for all possible shapes and sizes, and also on top of that we apply the unique triangle conditions which is given by this restrictions over the k1, k2 and k3, which boils down to this conditions in terms of shape parameters. So here in this work, our motivation is to estimate the spherically averaged bispectrum, for which we have divided our K space into spherical or circular, linearly separated circular bins, or rather spherical bins in 3D. And we compute the inverse Fourier transforms, those deltas and i's corresponding to each bin, and finally we compute the bin bispectrum for a combination of three bins which satisfy these unique triangle conditions. So here I am showing one of the sampling plot. For a particular size of the triangle and for a particular gridding and binning scheme. So these are the point on the MUT plane where we have the estimate of the bin bispectrum. And yeah, if you increase the number of bins, eventually you will increase the sampling of this MUT plane, as well as you also the time in the computation will also increase. Uh, uh, okay, so next we move on to validating our fast bispectrum estimator, for which we initially used the locally induced non-Gaussian random field, which we have generated using an underlying Gaussian random field with a power spectrum equal to given by a power law. And applying this prescription, we generate the non-Gaussian random field, onto which we applied our FB fast bispectrum estimates, and we compare the results against the tree level analytical predictions, which is given by this expression over here. And yeah, here are the results. You can see that the FFT estimates and the analytical estimates on MUT plane for this particular size is quite similar, as well as their values are also closer, which is clear by this plot, where we have plotted the difference between the FFT estimate and the analytical estimate in terms of 1 sigma error bar, which we have estimated analytically using this expression over here. So by looking at this map, you can see that at most of the place, this ratio is the value of the ratio is below 1, which means the FFT results are in 1 sigma agreement with the analytical predictions, except for this near squeeze limit squeeze limit case, where we expect the sigma b to be smaller. That's why this ratio is getting larger here. Here I'm showing again one of the slices from the previous heat maps for analytical and the FFT method for t equal to 1 and t equal to 0.73. Here the black dots are the FFT estimates computed from the 10 realization. The error bars are also computed numerically from the 10 realization, and this solid line is the analytical prediction along with the analytically estimated error bars. So as you can see that the FFT predictions closely follows this analytical predictions, as well as they are within 1 sigma error bars. Next we
Abinash,
again
sorry, you have 5 minutes.
Yeah, I will finish. Next, we have tested our estimator using a gravitationally induced non-Gaussian field, which means we have generated dark matter density simulations at these redshifts, 20 realization of that, and then we apply our first bispectrum estimator onto that and compared our result against the 2PT predictions, second order perturbation theory predictions. And yeah, here are the one of the results from there. So you can see that they are qualitatively similar as well as they are quantitatively similar, except for this reason where the 2PT basically under predicts the bispectrum. And in this plot, I am showing the relative deviation of this 2PT prediction with respect to the simulated bispectrum. So you, as you can see from this top rightmost panel, sorry, at z equal to 3 and k equal to 0.2, where the 2PT prediction is supposed to be valid, you can see that the fluctuations are random, and it is from the color bar, if you can see, it is within 20 to 30% fluctuations. And if we go down in, so if we go to the higher K1 bin, we can see that the fluctuations go down because the cosmic variance goes down. However, if we go onto the move on to the smaller redshift where the non-Gaussianity is larger, the 2PT predictions starts failing, and then due to that we are getting a huge positive deviation in this region, which is expected. So anyway, means only these of the plots are enough to say that our estimator is working well for this dark matter density field also. So next we move on to benchmarking our estimator, where we have compared our results for the dark matter density field with a relatively faster direct bispectrum estimator, which were used in this paper first. And yeah, here we are plotting the FFT results along with the direct DV results, which are shown in the red diamond. And you can see that the both of them are in agreement, in good agreement within the 1 sigma for the 3 redshift, and also they are in agreement with the analytical predictions in this smaller higher redshift where the non-Gaussianity is smaller. Next we compare next, in order to do the benchmarking, we have estimated the bispectrum using 2D non-Gaussian, locally induced non-Gaussian field, and we compared the time taken by the direct bispectrum estimator and the fast bispectrum estimator with respect to the number of grid in the simulation box. And here you can see that the direct bispectrum estimator scales as n to the power 4, whereas the this FFT bispectrum estimate takes time, which scales as n to the power 2. And this, there is a huge difference if you move on to the larger number of grids in the data. And yeah, so this is for the 2D. In 3D we have also tested this, and yeah, in case of 3D I'm not showing the plots because they are the similar. However, the deviation in the difference between the times in case of 3D will be even larger compared to this. So yeah, to summarize, the fast bispectrum estimator has an n cube order of n cube times improvement in terms of speed over the direct method. Here in this estimator, we consider all kind of unique possible shapes and sizes of the triangles. Our results are consistent with locally induced non-Gaussian field, and the dark matter density field deviations are within 1 sigma mostly. And yeah, needless to say, we are going to apply it to the EUR, the post-EUR signal, and post-EUR one is also already ongoing with some other people. So I'd like to stop. Thank you. I'll take questions or any comments.
Yeah, thank you, Abinash. So we now have time for questions. So if anybody wants to ask a question, please raise your hand in Zoom. You can also type in your questions on the chat box if you want. I will try to take them as they come. Yeah. Desh, please go ahead.
Yeah, I have a very naive question. When you talked of the orders in cube in the beginning, that n comes from what? The dimension of the matrix, or because you have a triple product?
This one, right?
Yeah.
Yeah, this is
Okay. So n cube is a grid size. Okay, total
Yeah,
number of
yeah.
cells. Yeah. Okay. All right. I just wanted to understand that. And then I have one comment, if it's allowed. You might want to try avoiding the edge effects because of the periodic boundary condition in the FFT, and see the improvement you might get in your process.
Okay, I'll check that.
Yeah.
Thank you for the suggestions. I've not.
Okay. Any other questions or comments? Okay, Obhirup, please go ahead.
Yeah. So, is there any? You said that for post-EOR work also it can be applied. So has it been tested in any data, whether it is a EOR or post-EOR?
We have not applied it to any data yet, but we are planning to apply it on the data soon with the Galaxy, some Galaxy Redshift survey data.
Okay. But this the data set which we have, like Ordnov has done for this UGMRT, can something be tried also for the post-EOR fast estimator?
Yeah, we can try it. Currently, we are validating our estimator, and yeah, it seems like estimator is doing a good job. So now we can try applying it onto the data or the simulations wherever you are.
Okay. Thanks.
Thank you.
Indulekha, please go ahead.
Yeah, if I understood correctly, the models will be going by the way the dark matter is behaving, while the observations will be following the actual gas. So we have this, core versus cusp, etc., for the potential minima. Will that, or how much will that affect these simulations? Can we account for that difference if it is there?
That is more like modeling question. So yeah, this is an estimator. So if there is any difference between the two models, if the estimator can capture, means I have not tested it against any different models of the dark matters yet, but yeah, this has been tested only on CDM model, on also on very large scale. As you can see, the grid size is more 2 megaparsec here.
Okay, thank you.
Okay, I guess we can move on to the next talk. So thank you, Abinash.
Yeah, thank you.
If you can stop sharing your screen. Our next and the final talk of the session is by Mohd Kamran, and he will be telling us about probing the IGM physics in the cosmic dawn through bispectrum. So Kamran, yeah, I will give you a warning at 10 minutes. Your talk is of 15 minutes.
Okay.
So you can
you see my screen?
We can see your screen, but it's not in a presentation mode, the slides.
Okay.
Now this is fine. Please go ahead.
Yeah, okay. So today I am going to present about bispectrum as a probe of IGM physics during the cosmic dawn through the 21 centimeter signal bispectrum. We know that the radiation from the first sources change the thermal and ionization states of the IGM, and these sources are not randomly distributed, rather they are situated at the biased locations. Okay. And radiations from these sources introduce high level of non-Gaussianity in the 21 centimeter field. And this nature of non-Gaussianity evolves with time as long as the different astrophysical processes like Lyman alpha coupling, X-ray heating, and ionization of the gas progresses. In mathematical sense, the non-Gaussianity means the signal among the different Fourier modes are correlated. So the 21 centimeter signal is highly non-Gaussian in nature due to the ionization, coupling, and heating of the gas in the IGM. So our main focus is basically in this work to capture or to study the non-Gaussianity in the cosmic dawn era. Okay, and in the cosmic dawn era, basically the sources of non-Gaussianity are Lyman alpha coupling, X-ray heating in the entire duration of the cosmic dawn, and ionization is also important here, but at the late stages of the cosmic dawn. So we know that a popular statistical measure of the 21 centimeter signal, which is the power spectrum, which is nothing but the Fourier transform of 2-point correlation function, describes a field completely only when it is a Gaussian random in nature. Otherwise, we have to shift our attention towards other higher order statistics. Since the 21 centimeter signal is highly non-Gaussian in nature due to different complex astrophysical processes, so one should head towards higher order statistics. So in this work, we will discuss, or we will talk about the first higher order statistic, which is the bispectrum. So bispectrum is nothing but the Fourier transform of 3-point correlation function given by this equation. And in this equation, B21 is our bispectrum estimator. Okay, and delta 21 is the Fourier transform of the differential brightness temperature in real space. From this definition, it is clear that the 3 K modes, K1, K2, and K3 involved in the definition form a closed triangle if and only if, in this definition, our bispectrum estimator will be non-zero if and only if the 3 K modes involved in the definition form a closed triangle given by this vector equation. We also know that the power spectrum, at least auto power spectrum, is always positive. On the other hand, the bispectrum can be positive or negative. So sign of the bispectrum is very important. So bispectrum can be positive if and only if either all 3 deltas in the definition of the bispectrum is positive, or positive, or 2 deltas are negative and 1 delta is positive. So combination will be positive. 2 deltas are negative and 1 is positive. So combination will be positive. Similarly, the bispectrum will be negative if and only if all 3 deltas are negative, or 2 deltas are positive and 1 delta is negative for most of the samples in the simulation box. So, yeah. So this plot represents the normalized bispectra, normalized in the unit of millikelvin cube. So evolution of the normalized bispectra with redshift. And this is the result of our earlier published work in MNRS. So this is basically represent the evolution of the bispectra from the cosmic dawn. Okay, for a fiducial source model where we have considered the Lyman alpha coupling, X-ray heating, and ionization, all 3 are running simultaneously from the beginning of the cosmic dawn. So most important thing that we have observed in our recent work, this is the sign reversal of the bispectra. So we have observed double sign change of the bispectra. One sign change is at higher redshift or early stages of the cosmic dawn, and other sign reversal is at lower redshift. So one sign change is from negative to positive, and another sign change is the positive to negative. So these 2 sign reversals of the bispectra carry much more information about the IGM physics. And also along with this, the evolution of the magnitude of the bispectra also carries about the information of the IGM physics. So to investigate the physical cause behind this double sign change, we extended our work by considering 1D radiative transfer grizzly simulation developed by Ghada et al. To simulate the differential brightness temperature at different redshifts. And in this work, we considered the sources of X-ray heating and UV photons, which cause ionization basically, are basically mini quasar and galaxies. Okay. So these are our basically fiducial model, and with so mini quasar basically having minimum halo mass 2 × 10 to the power 9 MSN, and and this table represents the different simulation parameters which we have opted in this work. Along with this fiducial model, we have also considered 4 different scenarios labeled as model A0, model A, model B, and model C. Where model A0 is a scenario where there is only Lyman alpha coupling in the cold IGM. Okay, and in model A, we considered ionization part also. So basically, model A is modified version of model A0, where we include ionization part also. And in this model A, or in this scenario model A, Lyman alpha coupling and ionization are running simultaneously from the beginning of the cosmic dawn. Next, in model B, we consider X-ray heating and ionization in the Lyman alpha coupled background. So in model B, Lyman alpha is already coupled, and And on the top of lambda alpha coupled background, X-ray heating and ionization are running from the beginning of the cosmic dawn. And in model C, we considered all three processes running simultaneously. So model C is basically actual or practical scenario, and model A naught, A and B are basically supporting artificial scenarios to investigate or to basically explain the features carried by the practical scenario or model C. So this is the output of the Grizzly simulation for scenarios model A, model B, and model C, where top panel represent the slices of the data cubes or differential brightness temperature at 5 different redshift from left to right. And similarly, middle panel represent slices of data cube for model B, and top bottom panel represent same for model C. So color codings in this plot are in such a way that the purple and brown regions basically represent the emission regions, and other colors represent the different level of absorption regions. So if we talk about the model A, then we can see that there is only absorption regions because there is only Lyman alpha coupling and ionization. So ionization is important at very late stage, but most of the time Lyman alpha coupling is important. So there is only absorption region for model A. But in model B, since there is heating on the Lyman alpha coupled background, so we can see that one important thing, up to a redshift 13, the heating contributes basically majorly to decrease in the level of absorption. And below redshift 13, heating causes the fast growth in the emission regions. So we want to basically see the impact of these features on the bispectra. And in model C, basically, if we talk about, there is a competition among the different fields, Lyman alpha coupling, X-ray heating, and ionization. Okay. On the other hand, in model B, there is no competition between Lyman alpha coupling and X-ray heating. So in model B, Lyman alpha is already coupled, and on the top of that, X-ray heating is going on. So our main task is in this work to probe these different IGM processes during the cosmic dawn through its impact on the magnitude and sign evolution of the bispectra. So first, it is important, or it is advantageous, that if we compare the power spectra and bispectra by one-to-one comparison. So this plot or top panel plots on the top panel represent the normalized power spectra in the unit of millikelvin cube. Bottom panel represent the normalized bispectra for equilateral K triangle or for all three scenarios at 3 different K1 modes. So we have opted K1 modes 0.2, 0.5, and 1 MPC inverse. So 0.2 to 1 MPC inverse range. So what we can see that the irrespective of K1 mode, the shape of the power spectra for a particular cosmic dawn scenario seems to be almost similar. Okay, but the shape of the bispectra differs with K1. Means that the shape of the bispectra have strong K1 dependencies. This is because the bispectrum probe the non-Gaussian feature, which inherently carries imprints of the different IGM processes. Okay, and these non-Gaussian features also depends on the length scales of the observation. That's why at different length scales, the shape of the bispectra are different. Next, I will discuss first only at a small K1 mode. So basically, small K1 mode is sufficiently large in this scale. So first, I will discuss for evolution of the bispectra for model A naught, which is represented here by black solid line. So we can see that the bispectra in the entire duration of the cosmic dawn are negative. Okay, this is because of there is only absorption region. So that's why there is so that's why all three negative products will form it. All three negative contribution of deltas form a negative value or negative product. So bispectrum will be negative in the entire duration of the cosmic dawn. But if we talk about model A, where we include the ionization part also, then we can see that the bispectra for model B agrees with that for, bispectra for model A agrees with that for model A naught. So you can see that here agreement of red color and black color curves agrees up to a redshift 13, because up to redshift 13, the ionization not much important. Okay, and below redshift 13, as ionization becomes important, then there is a disagreement between red and black color solid curves. This indicates that the ionization becomes important, and below redshift 11, the bispectrum becomes positive. Okay, so there is a sign reversal of the bispectra. On the other hand, in the case of power spectra, there is a magnitude difference. So bispectrum can constrain these features more better than the power spectra because there is a sign reversal of the bispectra from negative to positive. Okay.
Kamran,
Yes,
you have
yes.
5 minutes.
Okay, okay, thanks. So in case of model, if you talk about in case of model B, where the X-ray heating and ionization are running simultaneously, then we can see that the bispectra for redshift greater than 16 or at very early stages of the cosmic dawn, the bispectra is negative because there is the heating in the Lambda alpha coupled background, but heating is not much important up to redshift, let's say 15 or 16. But below redshift, as heating becomes important, then the bispectra first reverses, or sorry, first shows or first basically makes turnaround around redshift 15.6, and then it reverses its sign. Okay, so two different processes are occurring basically. First is sign reversal. Sorry, first is turnaround, and then sign reversal. Okay, so this is basically because the heating becomes important around this redshift, and as heating progresses, then the in positive direction, magnitude of the bispectra first increases and then it decreases, and again it makes another sign reversal. Okay, so around redshift, this means around redshift 13, heating causes a fast growth rate, okay, of the emission region around the source. So that's why there is a second sign reversal. So first sign reversal is happening when heating becomes important, and second sign reversal is happening when heating causes a fast growth in the emission region around the source. And in redshift between 13 and 16, in the redshift range between 13 and 16, heating majorly contributes to decrease in the level of absorption that I have already shown in the map, differential brightness temperature map. So if we talk about the actual scenario, model C, represented here by the green solid curve, again we see the double sign change of the bispectra. Okay, so this means that the heating caused the double sign change. Lyman alpha coupling is not responsible for the double sign change of the bispectra. Heating is responsible for the double sign change because here the Lyman alpha coupling and X-ray heating both are running simultaneously. And again, we observe the same shape of the bispectra as for model B. So this means the heating is heating causes the double sign change. Next, we extend our result for equilateral and squeeze square triangle at different K1 modes. So we can see that the evolution of the bispectra observed for equilateral K triangle for K1.2 MPC inverse, okay, also consistent with the squeezed K triangle at the same K1 mode. Okay, and also the squeezed K triangle bispectra also maintains the consistency of the result up to 0.5 K1.5 MPC inverse. So from these results, we conclude that the Lyman alpha coupling is not responsible for the sign reversal. Only heating process causes the double sign change. When heating becomes important, it causes first sign reversal. And when heating causes the fast growth in the emission region around the source, it causes the second sign reversal. And in the redshift range between these two sign reversals, heating majorly contribute to decrease in the level of absorption, which is clearly visible in the bispectrum. Hence, we can say that the evolution of the bispectrum sign along with its magnitude has potential to provide us with more insight about the IGM physics and also can be used as a confirmative test of the global signal detection. So the power spectrum is not able to probe IGM physics, IGM processes minutely, which can be better constrained by the bispectrum. So, okay, yeah, thank you.
Thank you, Kamran. So we have time for questions, and the first question will be by Kanon. Okay. Kanon, please go ahead.
Hello, Kamran.
Yeah.
Okay, very nice talk and interesting results. I just would like to understand the reason for your sign changes. So first sign change is you are saying that it is because your IGM is getting heated due to some X-ray heating.
No, not heated means heating becomes important means or heating means heating starts growing the basically ionized or heated regions around the source. Okay, so when heating becomes important means when heating number of photons are basically going to decrease the level of absorption first, and then it will increase the size of absorption region. Okay, so first sign reversal is basically caused by the when heating becomes important, because initially heating is number of source are very less. Okay, as heating progresses, the number of more and more number of sources will be get switched on. Okay, and up to redshift, basically there will be sufficient number of sources and not sufficient number of photons that will impacts on the bispectra through its sign reversal. Okay, and second sign reversal is basically when these heated regions these heated regions grow up in size very fast rate. Okay, yeah.
Okay. Okay. Just to understand, so the global signal also changes its sign. The global
Exactly.
signal.
Yeah. So global signal.
Yes. So
Yes.
do you did you check whether the redshift at which it changes its sign for the global signal coincides with your bispectrum sign reversal, or
Yes.
it is lagging? That's what my question.
No. There is not much lagging, because we are talking about here the bispectrum for large K1 mode. Okay, so at large K1 modes, basically the results are basically consistent with that for global signal also. Yes, there is not much lagging. Yeah, we have checked. I have checked this. I have already checked this. Yes.
Okay, O3, you can ask your question.
So can you hear me now?
Yes.
Okay. So I have two questions. So one is that how is your bispectrum, or is your bispectrum at all capturing the effect of Lyman alpha coupling? So this is the first question. And if it does not capture it, why is that?
So it means you are talking why the Lyman alpha coupling is not. No, it also captures the Lyman alpha coupling. So because if we talk about the model, let's say here model A, which is represented here by black solid curve. So here is the due to Lyman alpha coupling. Okay, there is an increase in the magnitude of the bispectrum in the negative direction. Okay. It also capture. Okay, and now if we switch to the model C, because there is a competition between the Lyman alpha coupling accelerating, so the magnitude is not going to be a larger value. Okay. There is a competition process. So basically, lower magnitude represent there is a competition between the Lyman alpha coupling and accelerating. So yes, it captures the Lyman alpha coupling.
Okay. Thanks.
Okay, Onion, please go ahead.
Yes, I have question about this double sign reversal.
Yes.
In the second case where the signal reverses the sign, I think you said that there was a growth in the heating regions. So my question is, how do this growth in the heating regions will lead to a change in the signal, lead to a change in the signature of the bispectrum?
Yes. So basically, you can understand it by the product of three deltas. So here the bispectra is positive, right? Why? Because there is also some large number of heated regions. Okay, but most of the IGM is basically at this redshift. Most of the IGMs basically include the absorption region, right? So at this redshift, or in redshift range between 16 to 13 also, two negative contribution from the absorption region and one positive contribution from the heated region, because heated region size is small and number density is also small. Okay, will be make a positive bispectrum. Okay, since the heating is beyond this redshift or below this redshift, heated regions are going very fast. So the scenario will basically get reversed. So two positive and one negative. Okay, will make the bispectra negative because heated regions are going now very fast. So two positive, one negative will make the bispectra negative. Okay.
Yeah, Desh.
Thanks. I have a naive question where the bispectrum itself is consisting of ingredients which are individually complex numbers.
Yes.
What is the nature of the bispectrum output? Is it complex, and what are you showing here, for example?
No complex, because we are actually taking the real part apart from the imaginary part. So basically, we are not taking here basically the complex number. Means first of all, basically we are making the product of these three numbers. Let's say delta 1, delta 2, delta 3, all three complex numbers multiplied. So this will also give a complex number, right? Product of three complex number will give another complex number. So from that new complex number, we are basically separating the real and imaginary part. Okay.
Okay, and what is shown here in these plots?
Yeah.
What real and imaginary parts shown separately?
No. In combining manner.
Okay, so how would the phase vary across this? Because the sign change to me is like 180-degree phase shift, and I cannot decouple that from. So there could be a smooth change of phase, and you might be, unnecessarily interpreting this as a big sign change.
Phase of means what? I didn't understand your question.
It could be a smooth change of phase.
No. Actually, we are not talking about actually phase of something, because if we product
but
three
phase,
deltas, and because we are talking about the spherically averaged bispectra, right? So there is no phase concept. So phase will be wash out, and there will be only magnitude variations of the bispectra.
Okay, so can I suggest that you take this offline?
Okay.
Yeah, I was also.
Can I say something? Basically, first of all, the bispectrum itself is a real quantity. Though if you take product of three visibilities or three Fourier transform of three K modes, what you will get, you are essentially doing an ensemble average. And when you do the ensemble average, as the signal is real, so essentially one half of the signal can be recreated in the other half of the Fourier space because of unitary condition. So that unitary condition essentially makes sure that the bispectrum, this product ensemble average of the bispectrum, when you are doing averaging over all angles, it will become just a real quantity. The imaginary quantity will cancel out. Any part of three visibility products will cancel out. So that's why the bispectrum is always a real quantity. That is first thing, and there is no phase because this K1 plus K2 plus K3 is 0. So that makes sure there is no phase involved in this thing. It just contains the amplitude.
Okay, so it's essentially a certain level of Hermitian symmetry.
Sorry, I cannot hear you. Can you repeat it again?
Yeah. So is it certain nature of Hermitian symmetry?
Yes.
That makes sure that this quantity is real.
Yes.
Okay. All right. Thanks. Yeah.
That is what it is.
So I'm sorry. I think we need to now. Yeah, we need to now end this session. So I suggest all the pending questions be taken into the discussions. I'm sorry about that. We have already overshot the time. So I think we can still try to come back 5 minutes from now. So around 3:40 or so. And so let's thank all the speakers of the session. And I now hand this over to the organizers in case they have any announcements to make. Thank you.
Okay, thank you. So let's meet at 3:45. It's 11. So let's meet after 10 minutes, 3:45. We will start our next sessions. Yeah.
Yes, Tapamada, you wanted to ask something.
Yeah, so we are meeting at 3:45.
Yeah, we will try to resume at 3:45.
Yeah, I think so.
Suman, can you stop the recording?